Hello, geometry. How are you doing? Hopefully well. Today we're going to look at a proof that is going to be very similar to one that may help us in a section of notes when we get back. This is also going to be a good review of all of our triangle congruence theorems that we talked about, I believe, in chapter 8. There were 5 that we talked about, and I'm going to write them off to the side real quick. There was side, 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 if you have all 3 sides in common. Then your triangles are going to be congruent. There was side, angle, side, angle, side, angle. Okay, the difference between here and here is that our angle is included, and here in ASA, our side is considered included. There was also angle, angle, side, where that side is not included. And then there was HL, which worked very nicely with right triangles only. HL stands for hypotenuse and leg. So right triangles only. So let's look at this picture. I see that I want to prove that triangle ABM is congruent to DCM. So as always, we're going to start with what's given. Well, in the figure I can see from these arrows, woohoo, right there and right there, that means that segment CD has to be parallel to segment AB, and also we have those markings right here that say they are also congruent in length. So I'm going to say that CD is parallel to AB, and CD is also congruent to segment AB, and that was all given. Okay, let's use the fact that we know that we have parallel lines, and we see that there's this transversal that's running through here. Okay, if parallel lines are cut by a transversal, we know that some angle relationships are formed. We know that there has to be probably some alternate interior angles, because I'm always looking for those. Those are nice ones. So I see this transversal cuts through, and I've got these alternate interior angles, angle A and angle D. They have to be congruent. So I'm going to say that angle A has to be congruent to angle D. We also have this second transversal running through here, this line CB. And hey, oh my gosh, we've got 2 more pairs of alternate interior angles at angle C and angle B. So that means that, angle C has to be congruent to angle B. And this was all done by the alternate interior angles theorem. And if we want to be, let's have some fun with it, we also have these angles here, this angle AMB and angle DMC. They have to be congruent because they are vertical angles. Again, vertical angles are angles that are formed by the intersection of 2 lines, and they are opposite of each other as well. So I know that angle BMA has to be congruent to angle DMC. Again, they are vertical angles. We have 3 pairs of angles, and now we want to figure out if these guys are congruent. We need to have some sort of side length being congruent, being in common, the corresponding side length, in order to show that these triangles are in like the same proportion. So, well, let's just use the fact that we have this segment A, B, and CD, and hey, that was already written down in our given. So we've got a side length in common. We've got a lot of places we could go with this. We could say that, because now we're on our final step, that ABM is congruent to triangle DCM. We could say that this is by angle, side, angle. All right, we've got an angle, an included side, and then an angle, angle, and an included side, and an angle. So we could say by angle, side, angle. You could even say by, let's get a nice color, you could say by angle, angle, side, right? Here's my side, here's my angle, here's my other angle, my angle, and then my side. So we can say this by angle, angle, side. Alrighty. Wonderful, wonderful. There will be something that looks very similar to this when we get back in chapter 12.3 or 12.2, all right? So look forward to that. Hopefully you are having a good day. Adios.